One of your classmates was asking me about this problem from the review sheet, which I did not have time to do. I had it prepared, but ran out of time. So it was actually, I think I actually had it on the homework. So directly we were asked to evaluate the line integral where the line was comprised of three separate segments. I think it did say that this would be easier if we used Stokes' theorem. So for this type of problem, a reminder, I do need to work out the curl of f. So I have set up the relevant 3 by 3 determinant, and it's actually pretty low stress. So the first component, we're taking a partial of this with respect to y, which gives us 0, and then minus a partial of this with respect to z, which is also 0. For the middle component, something similar happens. We get partial with respect to x of something which just depends upon z, and then partial with z of y cubed. That's also 0. It's actually minus 0, but since it's 0, it doesn't matter. But for the k component, the last one, I got a 3x squared and then plus a 3y squared, which you probably can't see. So, and I'm going to label that as g of s. Now, there are basically two ways that we could do this parameterization. I'm going to go with the one which I always use for something like a paraboloid or a cone, and that is r of u and v is v cosine u, v sine u, and then since this surface is z equals 1 minus x squared minus y squared, and I have committed to these being my x and my y, we're going to 1 plus this, well, sorry, 1 minus this squared minus this squared. So 1 minus v squared. Now, because it's only 1/4 of the paraboloid, the u's actually just go from 0 to pi by 2, and the v's go from 0 to 1. This is 0, and this is 1. So that's step 1. Step 2, partial RU is minus V sine U, V cosine U, and 0, as it always seems to be. What varies from surface to surface, however, using this type of parameterization, is that this partial is minus 2v. So I get to come back into focus the normal to the surface from the cross product of these two things. So I got a minus 2v squared and a cosine. Then I actually got a plus 2v squared and a sine, but that got multiplied by the negative from the cross product. And for the last one, I got minus v sine squared minus v cos squared, which gave me minus v. However, because of the orientation of this curve, the normal needs to be to our left. So the one I find easiest to focus on is going from here. So the normal must be where my left hand is. So we actually need the upward normal. So we reflect it by multiplying it by -1. So a required normal is 2v squared cosine, 2v squared sine, and then positive v, curl of f on the surface is the 0, and then I'm going to put in 3 times this squared plus 3 times this squared, which just actually gives us 3v squared. So the integrand is the dot product of these two things. So we're going to get a 0 plus a 0 and then plus a 3v cubed. So for surface integral 0 to pi by 2, 0 to 1, 3v cubed dv du, which is going to be separable. For the u part, we're just going to be kind of integrating 1. Now, that will give us a pi by 2. It's usually a 2 pi, but we've only got 1/4. And then for the power rule, 3/4 v to the 4. But it does have very user-friendly limits of 0 and 1. Hence, oops, 3 pi divided by 8. And please let us be able to see all of this. Okay, I'm going to pause this video. Now I'm resuming the recording. I've debated whether I should even do this, but it turns out that for this particular surface, the 1/4 of a paraboloid, the projection method actually works fairly nicely as well. So if I go with the projection method, then it's always an x and a y, and then this comes from the equation of the surface, which it is just, it's an alternate solution to the thing that I just did. Okay. Now, the nice thing about it is there's a standard formula for the normal to the surface, so I don't really need to work out the cross product. So it's partial of this with respect to x multiplied by -1. Same thing with respect to y. And then there is just a standard 1. And notice the difference in this one was that we actually got the required normal, the upward 1. G on the surface is still the exact same because x and y play the same roles. If this curl had a z in it, I'd need to replace each z with this here, but it doesn't. So the dot product of those two things is 3 times x squared plus y squared. What you need to be careful, however, is that when we use the projection method, we're left with a review of chapter 15, where in this case we have a double integral over this region here, because that's what we see when we look at it from above. Okay, that region there. And because that's like 1/4 of a disk, and because we've got the 3x squared plus y squared, it's probably advisable to use polar coordinates. So integral over r of that thing is 0 to pi by 2. Notice I actually did a 2 pi to begin with because that's what I need in 90% of these. 0 to 1, and then the extra r comes from dA. So basically you get the exact same thing that I got with this solution here, where I filled in the details. So, but if you're still listening, one of the reasons why I tend to, in general, prefer this type of parameterization for these paraboloids and cones, etc., is that if this is a cone, this changes to 1 minus the square root of this, and then these are no longer as nice as they are. And so in that sense, kind of the paraboloid, the upside down paraboloid, it's kind of unique that those also work well with the projection method. The others, like the hemisphere, the cone, actually don't work so well. Enough, Bert, stop.